We are starting off for Chapter 18 practice problems with some review from Chapter 5. So let's look at this. Using the delta H values, calculate the enthalpy change for the combustion of glucose. So we have glucose plus oxygen to give me CO2 and H2O. And we're told the delta H, the heat of formation, for the glucose and the carbon dioxide and the water. So to see how many kilojoules are produced for this reaction, we need to look at our mole ratios and do products. So how much are products minus the sum of the reactants. So I have my 6 times the delta H heat of formation value of water. So 6 times and plus 6 times the heat of formation of the carbon dioxide. And so it looks like I used my 6 times the CO2 first, plus 6 times the H2O. So we add those together, minus, now there's 1 mole of glucose here, and we know the heat of formation of that. It's negative 1273. Plus, and then 6 times the heat of formation of any element is 0. So we add that together. We get our add that together, and then do products minus reactants, and we get negative 2,803 kilojoules per mole for this reaction. Now that is for 1 mole of glucose to combust. But we don't want to know 1 mole. We want how many kilojoules are produced when 1 gram of glucose is produced. Well, if I have grams, grams can get to moles using the molar mass of C6H12O6. Add that up and I got 180.1752. So grams to moles, and then moles to kilograms using what we just found for delta H. So 1 times negative 2803, all divided by 180.1752. 3 sig figs because of my 1.00 should be negative 15.6 kilojoules are produced when 1 gram of glucose is burned. Number 2, using the heat of formation values, let's calculate the enthalpy change, delta H, for the combustion of methanol. So we're given methanol's heat of formation, carbon dioxide and water, and notice that the water's heat of formation is different than this water. And the difference between the two, notice the state of matter. This is a liquid, this is a gas, and so they are different values. But CO2 is a gas and a gas, those should be the same. All right, well, we're just going to do that same sum of the products minus the sum of the reactants. And so if I look at carbon dioxide, there's not a number in front of it, so that's 1. So 1 times that value plus 2 times the value of the H2O. So that's products minus reactants. There's 1 mole of methanol. And remember, any element is always 0. And so check your math, but I got negative 676.3. Number 3 wants us to calculate the amount of heat given off when we have 5.36 grams of ammonia that reacts completely in this reaction. So we can see that ammonia reacting in this whole reaction, the delta H is negative 939 kilojoules. Well, notice that this is 2 moles of ammonia reacting. We only care right now about 5.36 grams of ammonia. So I'm going to start with that 5.36 grams of ammonia. That's a 5. It was whole punched out. And I always want to go from grams to moles. So I found 1 N and 3 H's. And now the next ratio that I'm going to use is, we know that 2 moles of ammonia give off negative 939 kilojoules. So I'm going to use that ratio. And again, my moles needs to be on the bottom in order to cancel out. So when I do 5.36 times negative 939, all divided by 17.03 times 2, that answer, I should get negative 148 kilojoules. Next part is how much heat is evolved when 2.38 grams of water are produced. Well, again, we are told in this reaction that negative 939 kilojoules of water, or kilojoules of heat, is given off when 6 moles of water, but we are given 2.38 grams of water. So if I know grams, I can get to moles. Let's find the molar mass of water. So 2.38 grams, I'm going to go grams to moles. And then again, my next ratio, 6 moles of water produce negative 939. And I should get negative 20.7 kilojoules. Ended with 3 sig figs for both of them. Okay, let's get into chapter 18 problems. Number 4, we're told antimony, Sb, the heat of vaporization at its normal boiling point of 1440 is 195.4 kilojoules per mole. So, the entropy change when 2.05 moles of liquid antimony vaporizes at 1440 and 1 atmosphere is, so we're trying to find entropy change. All right, so we are vaporizing. We're taking Sb in liquid form and we're vaporizing it into a gas. Okay, now at equilibrium, and we can flip back to the front of this worksheet, at equilibrium, entropy change, delta S, is equal to delta H divided by T. And that's because G is equal to 0. So we also know that the delta H surroundings is the opposite of that. Well, let's plug in what we know. We know that our delta H is 195.4 kilojoules per mole. Well, I need this to be in joules, so I just times it by 3. And then divided by my temperature, I need to be in Kelvin, so 1440 plus 273. And so I got my S is 114.1 joules per mole Kelvin. And now that I know that, then we can use my 2.05 moles of liquid antimony, 2.05 moles, and then times that by 114.1 joules per mole Kelvin. So my moles and moles will cancel out, giving me 233.8 joules per Kelvin for my entropy change. Number 5, we want to predict whether the entropy change for each reaction would be greater than 0, less than 0, or too close to 0 to decide. Well, if we look at this first one, we have 1 mole of carbon dioxide gas plus 1 mole of H2. So we have 2 moles of gas on the left, creating 2 moles of gas on the right. So it's actually too close because there's the same number of moles of gas on both sides of the reaction. Let's look at the second one. I have 4 moles of gas on the left reacting to create 3 moles of gas. So my entropy is going to be less than 0 because our number of moles decreased. 4 moles in the reactants, 3 moles in the product. If we look at this example, notice that I'm going from a solid to a solid in a gas. So my entropy is going to be greater than 0 because I'm becoming more disorganized, going from a solid to a gas. Okay, so notice I've got gas, all 3 gases here. Let's look at our number of moles. 2 moles on the left to 3 moles on the right. So 2 to 3. That means that there is more chaos, more disorganization, greater entropy. So delta S is greater than 0 because our number of moles increased. And our last one, we have iodine plus chlorine. So 2 moles of gas on the left, creating 2 moles of gas on the right. So it's too close because we have the same number of moles on both sides of our equation. Looking at number 6, we're going to calculate the change in entropy for the reaction which urea is formed from ammonia and carbon dioxide. And we're told the standard entropy of urea. So we're going to look at our appendix in our textbook for all of the other values. So we were told that our urea is 174, And then I'm going to look up the entropy, the standard entropy values for ammonia and carbon dioxide and liquid water. So, found all of those. And then we're going to use that same idea, the same equation that we used when we found delta H. So to find delta S, we're going to take the sum of our entropy products minus the sum of the reactants. And it is mole dependent. That N stands for our moles. So I have 1 mole of urea, 1 mole of water. So I need 1 times this plus 1 times that minus 2 times our ammonia value plus 1 times our carbon dioxide value. And that should give us negative 356 joules per Kelvin. We are going to calculate delta G for the combustion of 14.1 liters of hydrogen using standard free energies of formation given in Appendix L. Okay, so the combustion of hydrogen. We've got hydrogen plus oxygen to give me water. So I've got a balanced equation. We're going to use that same idea to find delta G, which is the sum of the products minus the reactants. So looking at our values in the appendix, we know delta G. The delta G gives us free energy of formation for elements are 0. So then we can look up what water's is. And then we can do our the sum of the products minus the reactants to get our delta G value of negative 457.2 kilojoules per mole for the reaction. All right, so that's our delta G. Now, that is for 2 moles of hydrogen. We have 14.1 liters of hydrogen. So if we have liters of hydrogen, that's not going to help us much. In all of our other examples, we've always gone from grams to moles, and then we can say, okay, for 2 moles of hydrogen, we know the delta G, or the delta S, or the delta H. Liters. What am I going to do with liters? I got to get to grams somehow. Well, what we could look up is the density of hydrogen, because if I have liters, which is a volume, and I know density, I can find the mass of it. So let's do that. Or if I have volume, density is mass divided by volume. If I know density and I know volume and I can multiply those two together, I can find the mass. So let's do 14.1 times the density of hydrogen. And this is something that we would be able to look up. That means I have 1.2687 grams of hydrogen. And with that, I can now go from grams to moles, and then 2 moles of hydrogen, and I know my delta G for the reaction, giving me negative 149.85 kilojoules. Number 7 wants to know the standard free energy change delta G for the following reaction using values of enthalpy and entropy from the appendix. So I'm going to look up in the appendix and find the delta H values for nitrogen, hydrogen, and ammonia, and entropy values for nitrogen, hydrogen, and ammonia. Knowing that, I'm going to use the sum equations, taking my sum of products minus reactants for my enthalpy and for my entropy. So I'm going to do, for example, to find my delta H for the reaction, 2 times negative 45.9 minus, obviously 0 and 0 is going to give me negative 91.8. And to find my delta S, I did 2 times 193 minus 191.5 plus 3 times 130.6. So I got negative 197 joules per Kelvin. Then I can find delta G, because delta G is equal to our delta H minus T times delta S. Okay, so I'm going to plug in my delta H, negative 91.8 kilojoules, and I'm going to subtract my temperature, so 25 degrees, but it needs to be in Kelvin, so 298 Kelvin. Now remember, I need to have matching values. Notice that my S entropy is in joules. Let's make it kilojoules, so I'm going to move my decimal point back 3 spots. So T times S, make sure that S is in kilojoules, because we want G in kilojoules. So once you plug that in, check your math and see if you got negative 33.1 kilojoules. We want to calculate the delta G for the combustion of 1 mole of ethanol, C2H5OH, at 25 degrees Celsius. Use the standard free energies of formation given in the appendix. Okay, so I looked in the appendix and I found the delta G for ethanol, and for carbon dioxide, and for water. And of course the delta G for element is 0. So I used our summation to find our delta G. So I did 2 times the CO2 value plus 3 times the water value, got that answer, and I subtracted 1 times ethanol value. And so I got a delta G of negative 1,299.8 kilojoules per mole for the reaction. Now what if I only wanted to combust 2 drops of ethanol, which was 0.038 grams? So to work through that, if I know how many grams of ethanol I have, obviously I can go from grams to moles of ethanol, and then I can look at this and say 1 mole of ethanol in this reaction produced negative 1,299.8 kilojoules. So I can find the delta G for the combustion if I only had a small amount of ethanol. We are looking at number 9 now, and we want to find the equilibrium constant K at this 25 degrees Celsius, which is 298 Kelvin, for the following reaction. And we're told that the standard free energy change delta G is equal to negative 13.6 kilojoules. Okay, so we know delta G, we know the temperature, we want to find K, so what equation allows us to do so? Well, delta G equal to negative RT natural log of K. So let's plug in what we know. We know delta G, we know R, gas law, constant, and we know temperature. So I'm going to rearrange to solve for the natural log of K, so I'm going to divide negative RT from both sides. So we have the natural log of K is equal to delta G over negative RT. So let's plug in our delta G, and now notice I changed this to joules instead of kilojoules. Why? Because our gas constant 8.31 is joules per mole Kelvin. So I want my units to match. I could have moved the decimal back 3 spots for my 8.31. Either one wouldn't have mattered. So that's a negative R times temperature. Now that gives me 5.49 is equal to the natural log of K. Well, the opposite, so to get K by itself, to get rid of that natural log on both sides, we have to get K, we have to use Euler's number, or E raised to the 5.49. And E raised to the 5.49 gives me a K value of 242. Finally, number 10, we want to find delta G for the following reaction at 25 degrees Celsius and 1,000 degrees Celsius. And we want to relate this to spontaneity. Okay, so we need to look in our appendix and find our enthalpy and entropy values for calcium carbonate, or calcium oxide, and carbon dioxide. So once we have those, we're going to find, using our summation of our products minus our reactants, to find our delta H for the reaction and delta S for the reaction. And then we can plug it in to our delta G is equal to H minus TS, because we are changing the temperature. The temperature at 25 degrees Celsius, I'm going to add 273. So I found out what my delta H was and my delta S was. Remember, S is in joules, H is in kilojoules. So when we put it into this equation, we have to have our units match. And we tend to go to kilojoules since we're finding G. Okay, so at 25 degrees Celsius, which is 298, I'm going to plug in my H minus TS, and I got 130.9. That's a positive value. So that means that it is not spontaneous at 25 degrees Celsius. Let's plug in these values at 1,000 degrees Celsius. So at 1,000 degrees Celsius is 1,273 Kelvin. So if we plug in our values for that, I get negative 24.1 kilojoules, which means yes, it is spontaneous at 1,000 degrees Celsius. Now, what if I wanted to find the minimum temperature that this reaction would be spontaneous at? Well, we can set our minimum temperature by setting delta G equal to 0. So at equilibrium, we could say that T is equal to delta H over delta S. So at 1,121 Kelvin, it would be thermally stable until that point.